Today we will be looking at a Type 6 problem from the BC exam in the year 2000. Now it is from the BC exam, but there is nothing in this that is outside of the scope of an AB class. So AB and BC students can use this. It's Type 6 because it has slope fields and differential equations. So let's get started. On the axis provided, sketch a slope field for the given differential equation at the 11 points indicated. So this is a case where we are evaluating the slope at a given point, for example, 2, 1. This means we stick 2 in for x and 1 in for y, and we get a slope of 0. So at this location, we draw a slope of 0. In fact, all locations where y is 1, we're going to get a slope of 0. So we can go ahead and draw that for all of the locations where y is 1. If we did a second point, maybe at 1, 0, 1, 0, we stick 1 in for x and 0 in for y, and we get a slope of 1. Continuing to analyze our way through this, I notice that whenever x is 0, I will have a slope of 0. So anytime x is 0, we have a 0 slope. And we can continue to plug our way through filling out the points. We see that the slope is a little bit steeper here. The slope is negative when x is negative. And we have our point slope form. So this is worth 2 points. The first point comes from, do you have all of these 0 slopes where slopes need to be 0? And then the second point comes from, are these negative and these positive? And is there relative steepness there? So like the usual trend, 0 slopes are worth 1 and the rest is worth your second point. Part B says, use the slope field for the given differential equation to explain why a solution could not have the graph shown below. Or in this case, I put it off to the right. If this solution curve were to be placed on this graph, we would have a solution curve that has the 0 slope where it's supposed to, but you'll notice that the curve comes up and is not asymptotic to this 0 slope. If this curve were to fit on the slope field, here at 1, we should have a curve that comes up and flattens out and does something a little more like that. So in part B, the simplest answer would be the provided graph does not have 0 slope where y equals 1. Okay. You could also explain it using asymptotic behavior. There should be asymptotic behavior where y is 1 and this graph does not. But either way, a justification along those lines gets you 1 point. Part C asks us to find the particular solution. So this is your classic separation of variables. So if we have the differential equation dy dx equals x, y minus 1 squared, and we want to separate the variables here. First, we're going to move the y minus 1 squared to the left and the dx to the right. This is the separated state, so all of our y's are on the left and all of our x's are on the right. And now we want to take the antiderivative of both sides. The antiderivative of the left will give us negative 1 over y minus 1. This is kind of like saying 1 over u squared. We use the chain rule, sorry, not the chain rule, we use u substitution to find that antiderivative. The antiderivative of x is x squared over 2. And there's a constant on both sides, which I merge onto the right-hand side. At this point, we can plug in our initial condition. Our initial condition that they provided us was f of 0 equals negative 1. So when x is 0, y is negative 1. So we have negative 1 over negative 1 minus 1 equals 0 squared over 2 plus c. Therefore, c is equal to 1/2. So rewriting our equation, x squared over 2 plus 1/2. Okay. Our goal here is to solve this for y. So I'm going to jump over here. Negative 1 over y minus 1 equals, these have the same denominator. So by combining it into a fraction, what we have is one fraction equaling another fraction. And we can essentially cross-multiply this problem if we wanted to, or take the reciprocal of both sides. Let's do it this way. Negative 2 over x squared plus 1 equals y minus 1. So I multiplied the 2 to the left-hand side and divided the x squared plus 1 to the left-hand side, and then multiplied the y minus 1 to the right. Finally, add 1 to both sides, and we get the expression 1 subtract 2 over x squared plus 1 is equaling y. There is our particular solution to the differential equation. This is going to be worth 5 points. 1 point for separating the variables, 1 point for the antiderivatives, and 1 point for the constant of integration. Then if you consider the initial condition, that's going to be 1 point. And then your final solution for what is y, that's your 5th point. All right. One last piece, part D. What is the range of the problem? And this one takes a little bit more analysis, mental analysis. The range is going to be affected, essentially, what are the y values that this function can take on? And if you look and think your way through this, whatever number that we stick into x is going to either make this fraction approach 0, a very large number would make this fraction approach 0, or a number very close. Let me see if I can. Let's reapproach this. Okay, as x, when x is 0, this number is 2. And the further that we get away from 0, the larger our denominator will become, and a larger denominator will shrink the fraction down to essentially 0. So the biggest value that this fraction is 2, and the smallest value this fraction is nearly 0. So what we can do is we can say that we have essentially 1 minus 2 and 1 minus 0 are our upper and lower bounds. It definitely can have the 1 minus 2, so our lower bound for y is negative 1. It can get almost to 0, so our upper bound is going to be 1 minus almost 0. But since it never gets to 0, oops, that shouldn't be y. That value is 1. I struggle to find a better way to put this into words, but hopefully you're able to follow what I'm saying there. It's the last of the 9 points. So if you correctly found the range, you get your 9th point. All right, thanks for watching.